Namaste. In a couple of earlier videos, I had covered the topic of MGPT. This one of the major innovations that NCST had brought into the educational process, particularly in the programming space. As I had mentioned earlier, it was the early days of computing education in India. Not many avenues were available, and so the focus was on imparting quality computing education to people who want to migrate into software from maybe other disciplines or other areas that they've been working on. And so I mentioned, I talked about the motivation behind MGPT and how that whole process was administered in the part two. Today, I want to just kind of wrap up that topic, looking at asking this question: why do people think that, or why is there a belief that this is a very hard problem? And it's not just belief. If you look at the pass percentage, or if you look at the student reactions that time, it was uh, it was something that was very hard for them, and facing MGPT created a lot of tension and anxiety and all that. However, it was still appreciated because at the end of it, they realized that they are getting something which wouldn't have been possible otherwise. So, what is it that made this a hard problem, and why is this? Why was this important? So, when you learn programming in colleges or any programs, the focus is usually on the language. So we learn all the nuances of Java or C or C++, and so on. And second, conceptually understanding things like abstraction, encapsulation, object-oriented programming, modular development, and all that things we discuss in reasonable detail, but more at a abstract concept level. How does this actually come into practice, and how do we actually use this, and why is this important is hardly looked at. So the challenge that an MGPT student faced were threefold. One, the ability to to know what aspect of the problem statement is important for solving the problem and what is not. This is something very difficult to teach. It's kind of like learning to swim. Unless you get into the pool and figure out what is the best way for you to adapt, it is very hard to teach it by doing a classroom training. And I don't think the many institutions actually look at adapting or providing this skill. So this is the abstraction skill. Given a problem statement which may have a lot of relevant or irrelevant information, identifying the key information that is relevant to solving the problem and deciding how they should be captured in the system. Okay. The second problem was scoping and boundary cases. So when you are given a problem statement in college, you are possibly you will do some random input cases, and if it works, it's fantastic. Otherwise, people look at the code and say, yeah, you are trying to do something, and you might be able to get through the lab exam and all that in the process. But this is not really enough. So when I'm given a problem, this also I think I mentioned in one of the videos, that when I'm given a problem, you need to understand what is the scope of parameters that you need to look at. What are the boundary values? Like for example, if it is the favorite example of sorting, is it strings to sort, records to sort, numbers to sort? If it is integers, positive numbers, negative numbers, with duplicates, without duplicates, and all of that kind of aspects which are expected in the problem statement. If it is expected, your program should be able to do that. So creating adequate test cases to know whether your program is able to deal with all the cases that is expected in the problem statement was something of a challenge. Usually people have a lot of difficulty. So when they submit it to the Pariksha system, they will get three inputs are graded correctly, but two of them are wrong, and they have no idea what those two could be, because creating representative input cases for the entire range was something that was very hard for people to do. The third problem was debugging. So it invariably, all of us who write program know that when you write a program, it won't run the first time. There will be small or big problems. Major logical problems, if you are able to avoid, then you are pretty close to getting it running. But some problem or the other is inevitably going to happen. So we need to be prepared that when something goes wrong, we should be able to quickly identify where this has gone wrong and what is needed to fix it. This is a place where most developers are actually very weak. So you confident that your program is going to work the first time. So everything is there, no extra print statements, no debug help, no tracking mechanisms, nothing. You directly go from input to process and output. We have always recommended that when you write the program, one, structure the problem into, or your solution into modular units. It is easier to track whether your program, your control has reached at this point or this point, if you are organized in terms of methods, procedures, classes, or whatever the abstraction that you want to deal with. So the second is that whenever you enter and exit these major chunks of code, you should have some output coming in saying that, okay, yes, I am entering the sorting with this as the pivot, or I have this many elements have been swapped, or whatever. So some key information along with this entry and exit information at procedures would be very handy, because when you run the program and these printouts come, you read that printouts coming in the order, you will get a pretty good idea about how your program has actually worked, and you can match whether this is actually what you wanted it, the way you wanted it to happen. Wherever there is a mismatch, there could be a problem there. So we again know that half the job of fixing a problem is knowing where the problem is, what is the nature of the problem. If you make your program in such a way that the problem kind of comes out on its own, it is much easier for you to modify the program to fix it. But this very rarely happens, and this is one major challenge. So when something doesn't work, then you scramble, you put a print statement there, you put something here, you suspect something there, you make a more random modification and hope that things will kind of miraculously work. And this is one reason why lot of programs actually take a long time to get to a level of working stage. So the moment a bug comes, you panic, right? So maintain proper logs with proper messages, and when and what should they contain is something that you should think about. Key information. So putting out a big record as output is usually very counterproductive, but the key information at each point would be very good, because you should actually see a story coming out when you just look at the output traces. Maintain proper structure and modularity. This is ignored because you think that it's going to take more time to type in the code, and therefore you want to optimize it. Use good variable names and good procedure names, proper indentation, commenting. But when you go back to fix it, or when you want to go back to review things, this will make your your life much easier. And as the saying goes, today we don't actually write compiler optimized code, we write human optimized code. We should write code which people can read and understand, rather than write code which is very optimized for the program, because today's compilers are smart enough that they can figure out most of the optimization that you would have otherwise done. And so therefore use good variable names, good abstraction, so that it is easier for somebody else, it could be you yourself after a few months, to understand the structure and the flow. So more than programming, we should actually teach in our curriculum this problem solving capability. And when you do problem solving using a computer, we want to talk about computational thinking, that you think computationally to be able to tell your algorithm or your solution to a computer. And this is one place where people have a lot of difficulty. They say, yes, I know how to do it, but I don't know how to write it into a program. So this is actually where we should actually focus more on the educational process than trying to get into the nuances of programming language. So it is this situation that has made MGPT into a phenomena. So people have written poems and skits and stories and all that. And there was one of my friends who would say, who was running another institution where the course was run, that somebody who, after many attempts, finally managed to solve the problem, and in that dazed mode, he walked out of the office, breaking a glass door in the process. So all these tensions are completely unwarranted and not the intention at all. The intention was to learn this process of given a problem to a working solution, and that is what IT and computer science is all about. Now, even the experience of setting a problem for an MGPT was an experience by itself, because very often when we set a problem, we think that, oh, I mean, this is good question. This is very clear. It should be comfortable for students. When somebody actually tries it out, then you say, but are you assuming this or this? Should you want the output in this way or this way? And then you realize, oh, yes, I haven't actually specified that, or there are ambiguities which I didn't think about. So if you leave ambiguities in the problem statement, your students are going to go different ways. Your faculty program is going to test only one way, and then the whole exercise will get into trouble because students are going in one way, which is not ruled out by the problem statement, but the faculty has taken a different route. I mean, the faculty program or the gold standard that we talked about. Therefore, creating crisp, unambiguous problem statement itself is a big learning for many faculty who have actually set these problems. And as I mentioned somewhere, that we used to have a problem creator, test set creator, the pro coder who develops the faculty program, and guinea pig or a final testing. So we used to have this four entities, and usually they are completely different people. So this is one way to cross check, whether are you doing the test set that you are preparing, is that appropriate to the problem statement? All aspects of that problem statement is covered. Nothing outside is covered. So these are all aspects that we need to be worried about in problem statement and in the test sets. When you are writing a program, you should rely on purely the information that is given in the problem statement. Okay, if something is not available, there is a gap there, we should report back and that should be corrected. If there is an ambiguity there, that should be corrected. So we should not make any assumptions beyond what is given in the problem statement. Just because it is my friend who is setting the problem, we should not communicate any information except through the problem statement. So this all was a very, very big learning exercise for those who were inside setting the problem and creating the solutions, and to the student on the other side going through this whole process. That's why even on the net today, you can still find a lot of very senior people who are now 20-30 years before only they would have gone through these exercise. They coming back and say, yes, that was one thing which taught me how to program or how to think and how to do things. So not that we were teaching them, but we were creating a platform like a shallow pool for you to learn swimming. But we don't put an instructor there so that you actually practice it. You think and apply your mind and get through and learn swimming. So that's pretty much I'm going to talk about MGPT. Okay, if there are any questions that you want to post, you do. I will come back to that. Otherwise, thank you. That's it for now. Take care.